Galileo's experiments. Leaning Tower. It was Galileo, the foremost scientist of the early 17th century, who gave credence to the Copernican view of a moving Earth. He accomplished this by discrediting the Aristotelian ideas about motion. Although he was not the first to point out difficulties in Aristotle's views, Galileo was the first to provide conclusive refutation. Through observation and experiment, Galileo easily demolished Aristotle's falling body hypothesis. Galileo is said to have dropped objects of various weights from the top of the Leaning Tower of Pisa to compare their falls. Contrary to Aristotle's assertion, Galileo found that a stone twice as heavy as another did not fall twice as fast, except for the small effect of air resistance. He found that objects of various weights, when released at the same time, fell together and hit the ground at the same time. On one occasion, Galileo allegedly attracted a large crowd to witness the dropping of two objects of different weight from the top of the tower. Legend has it that many observers of this demonstration, who saw the objects hit the ground together, scoffed at the young Galileo and continued to hold fast to their Aristotelian teachings. Inclined planes. Galileo was concerned with how things move rather than why they move. He showed that experiment rather than logic is the best test of knowledge. Aristotle was an astute observer of nature, and he dealt with problems around him, rather than with abstract cases that did not occur in his environment. Motion always involved a resistive medium such as air or water. He believed a vacuum to be impossible, and therefore did not give serious consideration to motion in the absence of an interacting medium. That's why it was basic to Aristotle that an object requires a push or pull to keep it moving. And it was this basic principle that Galileo rejected when he stated that if there is no interference with a moving object, it will keep moving in a straight line forever. No push, pull, or force of any kind is necessary. Galileo tested this hypothesis by experimenting with the motions of various objects on plane surfaces tilted at various angles. He noted that balls rolling on downward-sloping planes picked up speed, while balls rolling on upward-sloping planes lost speed. From this, he reasoned that balls rolling along a horizontal plane would neither speed up nor slow down. The ball would finally come to rest, not because of its nature, but because of friction. This idea was supported by Galileo's observation of motion along smoother surfaces when there was less friction. The motion of objects persisted for a longer time. The less the friction, the more the motion approached constant speed. He reasoned that, in the absence of friction or other opposing forces, a horizontally moving object would continue moving indefinitely. This assertion was supported by a different experiment and another line of reasoning. Galileo placed two of his inclined planes facing each other. He observed roll down and then up the slope of the upward-sloping plane until it almost reached its initial height. He reasoned that only friction prevented it from rising to exactly the same height, for the smoother the planes, the closer the ball rose to the same height. Then he reduced the angle of the upward-sloping plane. Again, the ball rose to the same height, but it had to go farther. Additional reductions of the angle yielded similar results to reach the same height. The ball had to go farther each time. He then asked the question, if I have a long horizontal plane, how far must the ball go to reach the same height? The obvious answer is for a vert will never reach its initial height. Galileo analyzed this in still another way. Because the downward motion of the ball from the first plane is the same for all cases, the speed of the ball when it begins moving up the second plane is the same for all cases. If it moves up a steep slope, it loses its speed rapidly. On a lesser slope, it loses its speed more slowly and rolls for a longer time. The less the upward slope, the more slowly the ball loses its speed. In the extreme case in which there is no slope at all, that is, when the plane is horizontal, the ball should not lose any speed. In the absence of retarding forces, the tendency of the ball is to move forever without slowing down. We call this property of an object to resist changes in motion inertia. Galileo Galileo's concept of inertia discredited the Aristotelian theory of motion. Aristotle did not recognize the idea of inertia because he failed to imagine what motion would be like without friction. In his experience, all motion was subject to resistance, and he made this fact central to his theory of motion. Aristotle's failure to recognize friction for what it is, namely, a force like any other, impeded the progress of physics for nearly 2,000 years, until the time of Galileo. An application of Galileo's concept of inertia would show that no force is required to keep Earth moving forward. The way was open for Isaac Newton to synthesize a new vision of the universe. In 1642, several months after Galileo died, Isaac Newton was born. By the time Newton was 23, he developed his famous laws of motion, which completed the overthrow of the Aristotelian ideas that had dominated the thinking of the best minds for nearly 2 millennia. In this chapter, we consider the first of Newton's laws, a restatement of the concept of inertia as proposed earlier by Galileo.